Hello, welcome to the course Electronic System Design. Last few lectures we discussed about the PCB design using KiCad software. We started with some basic functionality of KiCad like schematic design, PCB design and then footprint editor and symbol editor. Then we saw some computational tool is there already in the KiCad where we specify the parameters and we can find out the width of traces and so on. Then we saw designing a real PCB using KiCad where we developed certain analog PCBs. Similarly, we can develop the digital PCBs which are, for example, we start with some digital functionality, we find out the function, we synthesize that using standard NAND gate or other logic gates. Once we have the logic of this circuit of this digital circuit and system, then we implement that in the schematic of KiCad and develop the PCB. So, in the same way what we designed for the analog circuits using op amp or 555 timer, we can also develop PCB for digital systems. And in digital system we discussed that there are certain issues when we design these for high speed PCBs where the signal frequency of these digital systems are high. So, that is digital PCB design for high speed circuits. Today we are going to discuss the extreme end of this digital design or analog design, that is RF PCB design. So, RF PCB design is nothing but the radio frequency PCB design. We are developing now the PCBs which are handling radio frequencies which are much higher, typically up to 300 gigahertz we consider RF. So, typically 300 to 500 megahertz to 300 gigahertz, this is the frequency range of RF signals and we want to develop our PCBs for this frequency range which is typically high. For even for high speed PCBs what we discussed those issues, the high speed PCBs are confined to 100 megahertz, 200 megahertz, that is the typical frequency of high speed PCBs. Now we are going to discuss RF PCBs where the frequencies start from 300 megahertz all the way to 300 gigahertz. So, that is a very high frequency range for which we want to develop these PCBs. And RF PCBs are now becoming very crucial because they have there we can use high frequency signals. It means the operation of these RF PCBs are very fast. So, earlier they were used only in some dedicated fields, for example, defense or the aerospace applications, but nowadays we are using RF PCBs even in the consumer electronics where we are transmitting and receiving the signals at RF frequencies. For example, consumer electronics, we have all our components, all our devices connected wirelessly. So, we need a RF PCB which is receiving these RF signals and sending these RF signals at that high frequencies where these RF PCB can radiate this signal wirelessly. We need not to have a wire connected, and these RF PCBs are becoming very important in day to day life. So, these RF PCBs we are going to discuss today, what are these RF PCBs and what are the critical parameters or what are the things we need to take care in designing these RF PCBs. So, radio frequencies PCBs, or in short we call RF PCBs. So, for these RF PCBs, the frequency range is typically 300 megahertz to 300 gigahertz. So, this is the typical frequency range of RF PCBs. These radio frequency PCBs have become one of the most critical and commonly used PCBs around the world. These RF PCBs are very well known in electronic industry for their capability to handle unique cases related to transmitting, receiving and controlling high frequency signals. These RF PCBs are known for handling high frequency signals and for the transmitting, receiving or the processing of these high frequency signals. These RF PCB design plays a significant role in the development of wide range of high frequency applications. Like wireless communication systems, radio devices and more. Earlier these RF PCBs were limited to military and aerospace sectors, but with the advancement of electronic industry, these are now commonly used in all day-to-day RF based applications. But now commonly used in consumer electronics. So we have these RF PCBs which can go up to 300 gigahertz, which is very high frequency range, and to make a wireless system we need to send these signals from one device to another device, and as we know, if the frequency of the signal is very high, the size of the antenna becomes smaller and smaller. So at this frequency range, the size of the antenna is very reasonable. We can put that on the RF substrate which can act like an antenna and transmit and receive the RF waves. So at low frequencies it is not possible to put the antenna on the PCB or in a handheld device because the size of the antenna is very big. However, if we go to RF frequencies where the frequency is very high, So the wavelength of these waves becomes smaller, so that the size of antenna becomes smaller, and we can put this antenna now on the PCB or the device itself. So nowadays we have all these handheld devices which can communicate wirelessly. So these are working at RF frequencies, so that the size of antenna is smaller. These RF PCBs have become now very much crucial in consumer electronics because we have mobile phones, laptops and all other consumer electronics which is wirelessly connected to each other. So RF PCB design is very much crucial nowadays and very widely used in electronic industry. So this is little bit about what RF PCB is and what is the difference between this RF PCB compared to our standard high speed PCB, where the high speed PCB is typically less than 200 or 300 megahertz. There the frequency of operation is high compared to our normal PCBs, but it is not in the range of RF, so that the signal does not radiate from the traces. So there we have some other challenges. Today we will see in the RF PCB what are the challenges we face while designing a standard RF PCB, which is very widely used nowadays in the industry. So we have some points for RF PCB design. For example, the first point itself is the material selection. Material selection is on what substrate we want to make this RF PCB. So most of the time when we design a PCB, we see a FR4 based PCB which looks something like green in the color. So typically all these PCBs, standard PCBs and high speed PCBs, these are made using FR4 substrate, which is fire retardant category of PCBs. Their primary goal is to support all these traces mechanically, so that we can make a circuit on the PCB. However, if we apply a very high frequency at the FR4 substrate, the losses occur in the substrate are very high. So we generally do not want to have a RF PCB which is working on very high frequencies to make on the FR4 substrate, because the loss of FR4 substrate itself is very high and it can attenuate the RF signal what we are sending. So we are sending from some signal from the source. That signal will degrade within the PCB itself and it may not reach at the antenna to transmit over the large distance. So the very first hurdle we face while designing RF PCB is the material selection, which material we want to go for, which is mechanically stable, over which we can route the traces, and the loss of this material is very less, so that our RF signal can propagate. Once we select these materials, let us say I want to go for some other materials like PTFE or some Rogers Duroid, there are certain high frequency PCB materials. The next point comes on the component selection, what component we want to choose. So component selection for RF PCB is very critical, because the same component, let us say 100 ohm resistor, the same resistor if we use for the high speed PCB or our standard digital PCB, that component can work, but if the same component we are putting in RF PCB and expect it to behave like a 100 ohm resistor, it may or may not be possible, because the size of these components and the parasitics it has, that may become critical for RF PCBs. At such high frequencies such as RF, the small parasitic capacitance or parasitic inductance present in the wire leads of these components, that also can create a issue at those high frequencies. So the component selection is also very critical for RF PCB design. We need to check out the components very carefully, so that the size of these components are smaller and we have less parasitics. So, this is one point which need to be carefully addressed while designing RF PCBs. Generally in RF PCBs, we do not want to go for the through hole components. For example, in the last discussions, we mostly use through hole components where we put the hole in the PCB and the resistance has two lead wires coming out. We put all these wires through the hole and solder it on the back side. For high speed or RF PCBs, we generally do not want to go for these through hole components because this extra length of lead wires can create significant parasitic capacitance and inductance which may be harmful for RF signal propagation. So, for RF PCB generally we want to go for the surface mount devices where the parasitic capacitance and inductances are smaller compared to through hole versions of these components. So, this is one point which we should take very carefully. The first is the material selection. We should choose the material where the RF losses are very less, and then the components should have very less parasitic capacitance and inductances. Next, we have a signal which is coming in, and generally when we apply a large signal on the RF PCB and frequency is very high, so there is some amount of heat dissipation or power dissipation within the PCB itself. When the heat is dissipated on the PCB, the temperature is going to rise of these RF PCBs. So, if the temperature increases, the properties of these materials and component that also changes. So, we need to keep our temperatures within control so that our material and all our components behave just like what we desired. So, the temperature management is also very key point in RF PCBs. This trace design, for example, the next thing is when we design these traces in digital design, if it is a not very high frequency design, we can have a minimum size of trace width and whatever signal we apply at the near end that reaches the far end. But in RF PCB, the width of these traces need to be determined very carefully, because in RF PCB the signal what we feed into these traces are not seen as a lumped component. For example, it is not a single resistance or single capacitance, it is looked as a transmission line where the characteristic impedance of this transmission line determines how the signal will be propagated from near end to far end. So, the width of these traces need to be carefully chosen. It should be calculated through the calculator tool which is there in the KiCad software. The impedance matching is another important point in RF PCB. When we send these signals from near end, let us assume that the characteristic impedance of the trace is 50 ohm, which is standard 50 ohm termination throughout the world. We generally follow the 50 ohm terminations. So, all the connections when we make in the RF PCB all should be terminated at 50 ohm characteristic impedances. So, whatever load we have, that is should be 50 ohm and that should be matched to 50 ohm characteristic transmission line, then the signal will not be reflected, it is perfectly matched. However, if there is a mismatch, if our characteristic impedance is 50 ohm and the load resistance is 40 ohm or 60 ohm, because of this mismatch 50 versus 40 or 50 versus 60, there will be some component of signal which will be bounced back at the far end towards the source. So, that reflection cause many problems. So, we need to have proper impedance matching in RF PCBs, and lot of issues of impedance mismatch comes from the vias. If we have a via and we need to connect this trace to a via. This via is generally not at the standard 50 ohm impedance. We cannot design that via so that its characteristic impedance becomes 50 ohm. So, whenever we route a RF signal, it is advisable not to have a via on the path. So, how do we design these RF PCBs? When we have a complete RF PCB where we have some RF signals to route, we have some high speed digital signals and some low frequency signals. So, the very first care should be given to the RF signals. Those RF signals should be routed on the very top layer where we do not want to put any via to bring it to the other side of PCB. So, first we route all the RF signals. The next step is we go for the high speed signals where these digital signals are typically in 100 megahertz, 200 megahertz range. There we try to avoid vias, but if it is not avoidable, we put these vias. There will be some reflection, but that is acceptable sometime. We route these high frequency signals using vias. We can go to other layers or the back layers for routing. And the third stage, we route these static wires where the frequency of operation is less than even kilohertz or even less. For them, placing the via is not a problem, so we can put as many vias as possible. So, this is how we route these RF signals and then high frequency signals. Grounding as well is the problem in RF PCBs. We need to have a proper grounding in RF PCBs. We will see how the RF field get terminated on the ground plane. So, we need to have a ground plane which should be running parallel to our traces. So, these are some of the points which we need to take care during RF PCB design. Let us write them down. So, this is a typical RF PCB. This is the photo of RF PCB. So, RF PCB design is more complex than standard PCB design. It requires careful consideration of following points. The first one is the material selection. So, here in this photo we have a sample RF PCB. So, we can see this RF PCB looks somewhat different than our standard PCB, where the inputs and any signal which comes on the PCB that come through this special type of connectors. For example, here we have these connectors, these are called SMA connectors, where this outer shell is ground, this whole outer shell which is connected here, and these are the two arms which are soldered here. on the PCB. So this whole outer part is grounded, and in between, if we see, this single wire comes from the center of this SMA connector and comes here. This is our signal carrying pin. The signal comes here and is applied to this IC through this track. This whole thing is made on some substrate. This can be FR4, it can be duroid substrate, or it can be PTFE. There are many materials available for these RF PCB design. This material should be selected very carefully. It depends on what frequency range we have. So first we decide our frequency range. First we decide what is the maximum frequency of our PCB, and based on that we find out the material which shows the least amount of loss for that frequency range. However, the cost is also associated. If we have very high frequency substrate we want to purchase, the cost is very high. So sometimes we need to balance between the cost and the loss we can incorporate. So the material selection is often the first point in RF PCB design. Next point is the component placement. So we will be using multiple components. For example, these are the capacitors we are using on board here. So we need to choose these components very carefully so that the parasitic components of these components, whatever we want to use, are very less and they do not influence our signal propagation. Third is the temperature control. The fourth is the trace design. Impedance matching. Via size. Loss tangent. Loss tangent is the how much loss will occur in the substrate for that particular frequency, that is characterized by loss tangent, that should be minimum. And grounding technique, which is very important for RF PCB design. And very important point to note in RF PCBs, every element of the design process, any of these points impacts the reliability and efficiency of RF systems. So every element or every stage in the design process impacts the reliability and efficiency of RF system. Whatever system we are implementing, any of these parameters, if not chosen carefully, that can impact the reliability and efficiency of that RF system. So let's discuss this one by one. So for this we need to first understand how the signal is actually routed in RF PCB. So we understand now how signal is routed. So unlike in digital PCBs, we have something called stripline and microstripline in RF PCB through which we propagate our signal. So this is the standard microstripline and this is the structure of stripline. In microstripline, which is very widely used in RF PCB, we have the PCB material shown by this yellow color. This is substrate. On both the side we have copper. On the bottom we have this copper completely filled the area. Generally this acts as a grounding plane. On top we pattern the copper area so that we make these traces, and this trace is running, let's say, from point 1 here to point 2, from one component to another component across this length. So this is the length of this microstrip line from point 1 to point 2, and this is the width of this microstrip. T is the thickness of this copper wire. Generally it's called cladding. So this is the structure of microstrip line where the signal travel from point 1 to point 2. This is very widely used. Also there is another structure very widely used is strip line. In strip line we have the substrate in between. On the top we have completely filled with copper, which is acting like a ground plane. This is complete ground connection. On the bottom also we have the ground plane, which is shown by this thin line. In between we have substrate, and we pattern, in between there is a copper layer. We pattern that copper layer to make a strip line. This line is also going like this in the middle layer. It's not on the top layer or not on the bottom layer, so I am drawing it by dotted line. This is the length of strip line from point 1 to point 2. It can carry the signal, and the signal will be traveling here across the length of this strip line. So this is how the strip line look like. These are the two ways how the signal propagates in RF PCB using microstrip or stripline. So, a stripline and microstrip are two different transmission line structure used in RF PCBs. The key difference between these two structures is the strip line is fully exposed to the dielectric material. Here we have this strip line. In the middle we have this strip line where the signal is going this direction, and this strip line is surrounded by this yellow dielectric material throughout its surface, top, bottom and sideways. So, this is fully exposed. Now, if my dielectric material is very lossy, then it will cause higher loss in the signal propagation in strip line, because this strip line is covered by dielectric from all the sides. So, if it is fully exposed and dielectric material is lossy, then it will face higher loss in the signal propagation. So, the dielectric material properties will have greater influence. However, on the other hand, microstrip, only one side, the bottom side is exposed to the substrate. On the top, this is exposed to air, which is typically a very low loss media. So, microstrip has lower loss due to isolation from substrate. However, the strip line has advantage of lesser noise, because if the surroundings are noisy, that noise can coupled to microstrip directly because there is no isolation from the environment. The top surface of this microstrip is exposed to air, to the open environment, and environment, if there is noise, that noise can impact the performance of microstrip here. The same noise have very little effect on my strip line because this strip line is covered from all the side by this dielectric material. So, this noise will have less effect on the strip line. So, the strip line has advantage to provide isolation from RF noise. So, this is how the signal actually propagates in microstrip. We have this microstrip and this is our substrate. On the bottom we have this ground plane. When we apply a electromagnetic wave or the RF signal here, this microstrip is coupled to the ground plane through this path. All these electric field lines will be starting from microstrip and going all the way to the ground for termination to all the directions. So, this is how the microstrip is actually coupled to the ground plane. Now, let us discuss microstrip as a transmission line, how it works. So, microstrip transmission line is very widely used in RF PCB design for connecting one component to another component and carrying the signal from one place to another one. So, this is the cross section of microstrip line, where we have on the top this microstrip line which is going, let us say, in the Z direction like this. And at this point we are applying our signal. This is, let us say, point 1, and from point 1 to point 2 we want to carry our signal. This is our substrate, and on the bottom we have this ground. Now, when we apply electromagnetic wave here at this point, the RF signal is nothing but the electromagnetic wave what we apply. So, this time varying electromagnetic wave will produce two fields. One is the electric field and one is the magnetic field. So, if we go back to electromagnetic theory, the electromagnetic wave, when it travels, it generates electric and magnetic fields. So, similar things happening here. When the wave is traveling from point 1 to point 2, this is going to generate the magnetic field, which is shown here by this dotted lines. This magnetic field is surrounding this microstrip across this entire length, and the electric field will be generated. Electric field or electric field lines, they will originate from the microstrip and they have to terminate at the ground. At other side, they have to terminate somewhere on the ground. So, one option is this microstrip line, when the electric fields are originating, they find the least possible path from source to the ground. So, this is one way where these electric field lines are terminating from this point to this point. When and they are originating on the top, some of the electric field lines will bend down and couple to the ground. However, some of the electric field lines may find some other ground in the surroundings or environment and will be terminating to that place as well. So, accordingly, we have the coupling of this ground with this microstrip which is dominated. However, some portion of these electric field lines are terminating to the environmental grounds or the outside ground. So, it means this microstrip has some amount of coupling to the environment as well. So, here we see only the bottom we have ground plane. So, majority of microstrip line is coupled to ground. However, some portion is still exposed to the environment, and if environment has certain amount of noise, that noise can impact these electric field lines, and accordingly our electromagnetic wave or the signal which is propagating, that will be impacted. So, this is how microstrip line actually works. In strip line, the top is also filled with this substrate. So, all the field lines, they terminate either on the bottom ground plane or on the top ground plane. So, they do not go outside and couple to the environmental ground. So, they are less sensitive to the environmental noise. However, these microstrip lines are easy to fabricate and easy to trim at the later stages. So, these microstrip transmission lines are popular in RF PCB design due to their simplicity and ease of fabrication. They consist of signal trace on top and a ground plane at the bottom. Separated by a dielectric material. the trace width, which is this width, and the spacing between two traces, and there are multiple factors also, these need to be very carefully designed. This, for example, this trace width determines the characteristic impedance of our transmission line. So, the trace width spacing and dielectric constant are critical for achieving the desired characteristic impedance. So, today we discussed two types of transmission line which we generally use in RF PCBs. RF PCBs are very special cases of our high speed PCBs where the signal frequency is very high, typically in the gigahertz range, and at those frequencies the losses which can occur in the PCB, the substrate material, are also significant, and we need to minimize that so that the signal can propagate without incurring these losses. We use two types of transmission line, one is the microstrip and the strip line, and we saw that microstrip line is easy to fabricate. Only on the top layer we need to pattern our trace. On the ground, on the bottom we have provide the complete ground. However, this microstrip is exposed to environment, at least half of the substrate is exposed to environment, and if there is a noise in the environment, that can directly couple to our microstrip. So, this is on the disadvantage side. In the strip line, however, is not so easy to fabricate, because in the middle layer we need to fabricate this microstrip line or this strip line, because whole of the surroundings are actually made using dielectric material. So, dielectric material we should choose carefully, it should not have very high loss, otherwise the loss will incur in the strip line signal propagation. But this strip line is not exposed to environment, so if environment is noisy, then that noise cannot impact our signal propagation in strip line. So, this is the basic difference between microstrip line and strip line. We generally use microstrip line because it is easy to fabricate and because of the simplicity, and we saw that the coupling of this microstrip line through the ground is through this substrate. So, substrate need to be having very less loss at those RF frequencies. We need to first determine our RF frequencies, and accordingly we choose the material, this dielectric material, so that the loss at that particular frequency is less and our signal can propagate comfortably. So, these are the two things we discussed today. That is all for today. Thank you.